Okay. Good morning, good afternoon, good evening, wherever you are. Thank you for coming, both for those who are here and those that follow us online. And I would like to start by thanking Anna-Katrine and Nick for organizing this event. I'm going to present some recent results from my own group. We work at the interplay between quantum theory and physics of space-time and try to employ operational quantum information tools to get insights in this interplay. I will tell you something about quantum reference frames in indefinite causal order, and I leave out Wigner and his friends for today. So let me go to the outline of the talk. I will first introduce, on the basis of simple examples, what I mean with classical coordinates. Then I will extend this notion to quantum coordinates and show two applications of the quantum coordinates, namely in description of superposition of semi-classical spacetimes and indefinite causal order, and at the end I will conclude. So half an hour is not long, so let me start immediately. Imagine that you have just two objects in the world. There is this kind of Earth, a larger object, and a small object, like an atom, and there is nothing else. And assume that there is a translational invariance, that all interactions depends only on the relative distance between these two objects. Now, usually, if we want to solve some problem, concrete problem, we introduce a coordinate system. And by introducing a coordinate system, we immediately introduce something which we can call gauge degrees of freedom. So degrees of freedom that are not really physical, because they are just two objects, only the relative distance between them matters. But then we can think that there is some kind of hypothetical imaginary observer at the origin of this coordinate system that could measure the distance from this origin to the position of the two objects. But still, we should bear in our mind that all what is relevant in the end will be the relative degrees of freedom. Now, because the coordinate system and the choice of the coordinate system is irrelevant, sometimes we pick up exactly those that simplify the problem. For example, maybe the most simple situation here, if we center the origin of the coordinate system at the center of Earth. Now, the reason why we can choose arbitrary coordinate systems is that we have this big idea of the theoretical physics that the physical laws preserve their form or are invariant under the choice of the coordinates. Or a typical example is, for example, Newtonian gravity that is invariant under translations, or maybe Einstein's field equations that are invariant under most general coordinate transformations. Now, that's all what I want to tell you about classical coordinates. And now I move to extension to it, which I follow here the ideas of Giacomini et al. Paper from 2019. But I'm going to read this paper in a different way, and this for the first time now. Namely, I will talk about, again, just two objects in the world. It's again a mass it's again the Earth and the small atom. But now I will start from a certain coordinate system that I indicate this again with this hypothetical observer at the origin of the coordinate system, such that the state with respect to this coordinate choice look like superposition of the position of the Earth and maybe localized position of the atom. And now what I want to do is to move into another coordinate system, and this is the state with respect to this coordinate system, namely the coordinate system in which I will put the origin at the center of the Earth. And now I can ask myself, how should then two other objects, one which is just hypothetical, and the other maybe that is real, how should they look like in this coordinate system? And what we proposed in 2019, that they should get entangled, they should look entangled. And it's easy to see this because If you are in this branch of the superposition, then B is just right up and C is just right down, left down. So it's exactly these two positions of B and C. But if I'm in the right branch, then the B is left from me and C is even further away from me. So that's these two possibilities. And indeed, one can formalize this and introduce the exact unitary transformation that will change the state on the left to the right-hand side. And it looks like that. It involves A, C, and B systems, and it can be understood as A, you first read where A is, and then you push by the generator of translations the B to the extent where A is, and at the end you just exchange C and A with this reflection symmetry. And indeed, if you do that, you will get as a final state a state that is entangled between the C and B, because how much you push the B depends on where A was. And that was the idea of this quantum coordinates or quantum reference frames. And again, you might ask yourself, well, what is this meaning of this entanglement between something which is a gauge degree of freedom and maybe some real systems? And I would say it's nothing else than what you have in the classical coordinates. It's imaginary coordinates that help you describe certain systems, but at the end of the day, you will concentrate yourself only on the physical degrees of freedom. And indeed, it's a helpful thing, because from something what on the left-hand side seems to involve the superposition of space-time, you get on the right-hand side with something which has a definite space-time. And now that's exactly the problem that I will want to investigate next, and to see if these tools can help me treat the situation we have a superposition of semi-classical spacetimes. And what I consider here is, again, in some coordinates, a mass to be in a superposition of two positions, and maybe a clock that is localized, and think how this clock will now tick in this superposition of spacetimes. And what we, Anna Katrine, Victoria Kabel, and Esteban, and myself suggested in a recently published paper in 2023, that we can go into suitable choices and coordinates such that something which looks like a superposition of space-time go into the definite space-time, where we will be able to solve the problem with the conventional quantum field theory on a curved space-time, and solve the problem, and after solution go back. And the reason why we make this step is, again, the belief now that the physical laws preserve their form, even not only under the usual classical coordinate transformations, but also extend to quantum superpositions of these coordinate transformation. And here is the sketch of this proof, and then I will go through this. Namely, we start with this situation in which the mass is in a superposition, the clock is localized, and there is this hypothetical observer. And then via reference frame transformation, we, so to say, jump on the Earth, or choose the coordinate system in which the Earth is an origin, in which case the two systems become entangled. Then we solve this problem, and we know that where we have now a clock in a superposition of two positions, that the ticking rate of this clock will depend how far we are from the mass. We can solve this problem with conventional quantum theory on a curved space-time, and then go back into initial reference frame and provide the answer that was not immediately clear because we had to deal with the superposition of space-times. So how do we do that? Well, we choose this origin at the hypothetical observer. We have a superposition of mass, and then we have 2 degrees of freedom for the clock. One that tells me where the clock is, and the other is internal degree of freedom. This is exactly what is ticking. So it means that this internal degrees of freedom, it must be in some superposition of energy states in order to be dynamical, to tick. And in the simple case, these are just 2 energy levels. And then I move to another reference frame in which, as I said, the situation will be such that the 2 systems C and R will get entangled, and the internal degrees of freedom is still factorized out. And so we start with this system, and now we can solve this problem, for example, using some ideas from our group from 2011 of Zich et al. Paper, in which we have a single clock in a superposition of two positions, and then we see that the ticking rate will depend. The closer you are to the mass, the slower the clock is. And once we solve this, we can go back into initial reference frame. The way how we solve this is using this paper, namely, you will see that there are two effects. One effect is this time dilation. So the pointer of the clock will depend on the proper time elapsed, which again depends on the relative distance between the clock and the mass. And there is another effect that is a cumulated phase for the two amplitudes, which again corresponds to the accumulated proper time. And so once we have this, we can go back to the initial reference frame or initial coordinates, in which now the mass is in a superposition, but the clock is localized, ticking in this superposition of two ticking rates. And inverse transformation brings me to the final state, in which I have the effects of time dilation and the phase accumulated. Okay, so that's all what I wanted to tell you about one example where we apply this. And then the next, and now for something completely different, actually is not completely different. It will be related to quantum coordinates and indefinite causal order. And so just to remind you about the indefinite causal order, there is a series of works now, all already 10 years old, in which was proposed that quantum mechanical superpositions can be extended also to the causal order, to the situations in which we don't have well-defined causal relations between events, and we can speak about superposition where A is before B or B before A. The first explicit example was worked by Kiribedala et al. In an example of the quantum switch, and so far we have been discussing in the literature two realizations of this indefinite causal order. One is due to superposition of trajectories in Minkowski space, and this has been realized here in Philip Walter groups, where you have in one branch a photon going first to A and then to B laboratory, whereas in the other branch it goes first to B and then A, and then we put this in a superposition, and the quantum switch means that we can apply, depending on the path, degree of freedom, which is the quantum control, the two operations in different orders on some target qubit. Another realization of that is in superposition of spacetimes, where the control is actually the large mass that can be put either closer to Bob or closer to Alice laboratory, and this mass will induce certain time dilation in the respective laboratories that is so large that the signal can travel from one side to another and come in time, so to say. And therefore, we have a superposition of causal orders. And again, if there is a photon or some other test system exchange between A and B, we can have a realization of the quantum switch unitary. And there is still going on a huge debate: what is the real quantum switch, optical or only gravitational? And I want to a little bit tell you about this question. And so now, having said previously that the choice of quantum coordinates can move you from the superpositional spacetimes into definite spacetime, so we can render the spacetime metric definite by quantum controlled diffeomorphisms, we may then ask ourselves, well, if the space metric determines the causal structure and can be rendered definite, maybe this applies also to the quantum causal order. Namely, can we always find quantum coordinates in which causal order becomes definite? Or can indefinite causal order be a quantum coordinate artifact that with the right transformation can be transformed away? And the answer to this question is no. And I want to convince you in the next couple of minutes that the answer is no. And in order to tell you, I have to tell you something about the work that has been done with Anne-Catherine, Victoria, Marius, and myself. I didn't put the citation, so I say it now. And for that, I want to introduce the general relativistic notion of the event and the causal order. First of all, think about these trajectories being the trajectories of Alice's laboratory, Bob's laboratory, and a test particle that is flying in between them. And now we define the events as the coincidences between the crossing points of two different fields, if you want. So interaction of Alice's laboratory with the test particle will be epsilon 1, and Bob's laboratory particle epsilon 2. Now, what we will use to introduce the notion of the causal order is the proper time, also for the reasons that proper time is something which is diffeomorphic invariant. And we will orient this, parameterize the gamma 0 curve and time oriented such that time goes in positive direction from the initial point to the final point. And now we will use the proper time in between elapsed in between the two events, epsilon 1 and epsilon 2, to define the causal order. That's the way how we define the proper time. And I want already now to tell you an important element of that this proper time depends not only on space-time metric, but also on the trajectory. And we will see that in one case we make use of the fact that we put spacetimes in a superposition to achieve the indefinite causal order. That will be the case of the gravitational quantum switch. But in the Minkowski space, we can still make use of the superposition of trajectories to achieve the indefinite causal order, although the metric is always the same, and flat and Minkowski. And now, the exact quantity that we use for the causal order is actually the difference between elapsed proper time t2 minus t1, and more specifically, the sign of this difference. And then we will say that if this event is before the second one, then the sign will be positive by the convention how we oriented this curve. And if we have the opposite case, then the sign will be negative. Can you tell me? It's 10 minutes. 10 minutes, okay. So I will leave some time also for the questions. And now we will define the causal order defined by the sign of this S. That meaning that if it is a positive, we will say that Alice is before Bob, or if it's negative, Bob is before Alice. Now let me move into the superposition of the spacetimes. What I mean with this notation here, that in some quantum gravity theory, we will go into the semi-classical limit in which the states of the metric will be some very central, localized around some coherent states, and all the uncertainty around coherent states can be neglected, so I can really think about these two distinguishable and orthogonal states. Now, if we think about this superposition of two spacetimes, then we can associate to each the branch one manifold equipped with a metric, and also the sign of the causal order, and another manifold, again, equipped with a metric and the sign of the causal order. Now, the most important thing is that although we have 4 space-time points on the manifolds, they have little physical meaning unless we identify them with the coincidences between different fields. So if I think about the event epsilon 1 as being the crossing point of Bob's laboratory and the test particle, then I identify this point in one manifold with the same event, namely the crossing of the laboratory of Bob and test particle in the other manifold. So physically these are the same or identified across the manifold's points, giving rise to just 2 physical points, although of course in each manifold they are put at some arbitrary space-time point in one manifold and the other manifold. And now, after I identify these events, I can ask myself for each branch whether I have a positive or negative sign for the difference of the proper times. And so we will end up with 2 possibilities for the sign of the product of the time differences. If in both branches Alice is before Bob or Bob is before Alice, then the sign is the product is positive. But if we have an opposite causal order, in the two branches we will talk about indefinite causal order. And now we know that the proper time and that the sign will be, of course, invariant under diffeomorphisms. The thing here is an extension of this statement, namely that even if we use the quantum coordinates or the quantum diffeomorphisms, or in another way, if you apply different diffeomorphisms in different branches, the causal order will still be invariant under that. So there are two statements that I want to finish this talk, namely that in our view there is no genuine indefinite causal order in the sense that gravitational switch is the real one and optical is not, because according to this definition in which we identify the same physical events in both branches, we in both cases have the property that the product of the sign is -1 and we have indefinite causal order. And furthermore, causal order cannot be rendered definite even by the most general quantum diffeomorphisms, namely those that, depending on some quantum system, that is a quantum control, I can apply one diffeomorphism in one branch and the other diffeomorphism in another branch. For example, if I have in one manifold this situation and another manifold this situation, I cannot then map these points, A point, epsilon A point from one manifold and epsilon A point to another manifold with two different diffeomorphisms on the same manifold. And once I identify these 2 points, I will see that I will also manipulate the curves such that the indefinite causal order is preserved. And maybe it's really chaotical lines here, and you can't see, but I will drive you through at least just for one case. You can think about the black line as really this black line where I go from Alice to Bob's laboratory. But if I apply a different diffeomorphism for this picture, this will modify the black curve such that if you look at the black curve very precisely, it goes like that. So it goes first to the upper lap and then to the lower one and then go out. So indeed the causal order is reversed. And I'm coming with this to my summary. I want to remind you that we introduced quantum coordinate transformations in which it was necessary also to have some gauge non-physical degrees of freedom. And by changing the coordinates, we succeeded in changing the superposition entangle between gauge and the physical degrees of freedom. But that was nevertheless useful in the sense that by assuming that physical laws preserve their form, even under this quantum coordinate transformation, we could solve some problems that could be at the first sight be problems outside of the regime of the well-accepted physical theories. For example, when we have a superposition of masses producing different ticking rate of clocks around them. And at the end, I introduce a notion of indefinite causal order, which could encompass both optical and gravitational quantum switch. And at least this shows that if you accept the gravitational quantum switch as the realization of the quantum switch, you should accept also optical. You either accept both of them or you reject both of them. And finally, we could show that indefinite causal order is invariant under these most general quantum coordinate transformations in which you can apply different transformation in different branches. And with this, I would like to thank you for your attention.
Thank you, Časlav, for your talk. I will open the questions with one question that was posted online from Samuel Fedida. Since the identification of points across superposition of manifolds is not unique, can you not find different maps of points that give you different orderings of events on a single manifold?
I would say that it is unique. It's defined by the events, physical events of the crossing between these two fields, and that's If I go back to the picture, there is no other possibility than identify this point with that point, because these are the two identical physical events.
Yeah, Thomas?
I have a question about the kind of principle of covariance that you use at the start of the talk. So in quantum mechanics, I'd say that there's, if your change of reference frame, if you change commutes with the Hamiltonian, then you have some principle of covariance if the Hamiltonian is the same before and after. So the same equation of motion. So I was wondering, why do you need this as an extra assumption? Could you just check that your unitary change of reference frame to this superposition and commute with the Hamiltonian? And then if so, then you've shown that there's kind of a principle of covariance, right?
Yeah, I think this is the way how to do this. I don't know what I'll try to get if I have actually something about that.
Yeah, exactly.
Exactly. So, yeah. So that okay. This is the definition. So indeed. So I would say that you start with some Hamiltonian, let's say. From the initial Hamiltonian, okay, from the point of view of C, so the Hamiltonian is about A and B. We didn't have this very complicated situation so far, but I introduce now that it could be a Hamiltonian that involves all external systems. And then if this transformation is a time-dependent transformation, the Hamiltonian will change in this way. But if at the end I get now for another systems, B and C, the same functional form of this Hamiltonian, I would say this is a symmetry, and I would say this is then covariance is, or invariance of the physical laws is preserved, yeah. I would say this is the most general formulation in Hem, yeah.
So in a sense, it's not really like an extra assumption, because you can just kind of show that this holds.
You can show it's called, or it might be that it's not like that. Yeah.
Any more questions?
I may just add that sometimes it's very surprising things that if you start, for example, for the free particles on B, and you make a quantum translation, you will not get two free particles. So it's not trivial what Hamiltonians preserve this symmetry. Yes?
So, I obviously like a lot the last ideas because I'm a co-author on the paper. But the most general quantum theory, not really, right? Because we don't know what to do with the conjugate and so on. We don't know that it's the most general. That's a good...
Yeah, I don't know whether it's the most general. In the framework of what we do, which are the states of superposition of semi-classical spacetimes, it seems like then you really go branch by branch, and within one branch you can do normal diffeomorphisms. But if we go beyond this semi-classical approximation, I think they are much more general transformation.
Any more questions? Yeah, I think then we can move on to our next speaker.